So it's my great pleasure to welcome Stefano Giangelo tonight. Stefano is a music DSP researcher and engineer specializing in virtual analog modeling. Stefano has been in the field about 10 years and is the engineer behind Artura's virtual analog models of classic analog synthesizers, including Buchler's Music Easel and EMS Synthi. More recently, Stefano founded his own DSP consultancy called Orastron. Earlier this year, Orestron released a library of DSP modules in order to assist companies in developing custom audio DSP applications. So Stefano is going to show us an example of those modules in use and speak to us about the process of developing engines for audio hardware and software. Over to Stefano.
Thanks. So, yeah, thanks for the introduction. It was perfect. And let's jump right into the presentation. If I can manage, can you see it?
Yes, we can. And just to let people know, if you have any questions, please feel free to ask them in the chat. Just please precede them by the word question so I can see them very clearly. And we'd love to hear any questions, no matter how beginner or advanced you may be. Please ask away. Take it away, Stefano.
Okay, thanks. So I've been already introduced, and I just want to say that this talk is about developing engines for audio hardware and software, which is what I do daily, actually. So actually, this presentation will be split in two parts, one of which is very boring but necessary for the second part. The very boring part is about my history, and this will be preliminary to the technical part, which is maybe a little bit more into the things that are of interest for us, but we will talk about it later. So I'll try to be as how to say, unembarrassing to myself as possible, but let's go. So this is my story. Let's say I started taking a computer engineering degree from the Polytechnic of di Torino, which is in Turin, northern Italy, in 2010. In the same period, more or less, I was participating to some free and open source software projects, and that's something I'm not particularly proud of because of how those things turned out. But anyway, there was some audio stuff that was being done. Then from 2011 to 2014, I moved to Finland, to Helsinki, to get a doctoral degree in acoustic and signal processing under the supervision of Professor Vesa Välimäki, who is a huge name in music DSP. Then when I left, I went working at Arturia in Grenoble, France, and I've been the lead DSP engineers for 3 years there. Then I left because I'm a little bit of a mad person. I went back home to southern Italy where things are much more difficult and started freelancing. And I've been very successful with the freelancing stuff. So last year I also started my own DSP firm, still here in Italy, in this small town in the south. I am the author of 12 international scientific papers, and I'm also officially recognized by Italian and French authorities as an expert in the field, also for research tax credit purposes in France. So if you have a French company, feel free to contact me. You'll have some tax credit. So let's start with Arturia, because I did my studies, and those were studies. I mean, you can find out stuff very easily if you're interested. I've been working, as said, in Grenoble, France, which is a weird, yes, but also a very nice place. It's a very small town close to the Italian Alps, Italian-French Alps. I don't want to take ownership of the Alps in the name of my country, of course. And I've been working on some interesting projects like the Buchler Music Easel, which was mentioned before, and other things back then. Then I have to say that the people who were working there were exceptional in many ways. There were people who were capable of incredible things, especially in the hardware department, like the people who designed Polybrute now, but was the Matrix brute back then. It's unbelievable people. And the organization is very good as well. And indeed, now the company has grown much bigger than it was at the time. But as I said, I'm a little bit mad and I wanted to be independent at all costs, mostly to do two things, to do more things that were related to the DSP work. So I wanted to do more different things, and some of them more in depth, at least more than it was possible back at the time. So as I said, I went back home and I started freelancing. This is the main square of my hometown now. It's 400 people village with 350 people older than 65 years old, probably. So it's a very small town. I'm doing virtual analog stuff as the things that I've done with Arturia, mostly classical synthesizers and guitar effects. I'm also doing some custom DSP algorithms from time to time. I've been doing some wavetable synthesis stuff, some dynamic processors, tuners, and other stuff. I'm back into academic research since I left. I've been doing some work on anti-aliasing methods, sound extrapolation, special math functions, and whatnot. And from time to time, I go consulting, teaching, do workshops, anything that's connected to the usual stuff. My current clients include Arturia, which everybody knows, I guess, Neural DSP, which is a company that's doing great stuff in guitar effects, both software and hardware. Dark Glass Electronics with bass gear, both pedals and amplifiers. Elk, which is a Swedish startup that does some extremely low latency remote jamming stuff. And this activity actually allowed me to gain some insight on how projects are actually managed, how the specification process work, how the implementation of all the components actually is laid out, and then in general, how management of the projects is implemented usually. But this also meant having greater responsibilities because, of course, now I'm on my own. I need to respect all deadlines. Then there is the state, then there is the administration, taxes, and whatnot. So it's much more work than before. Then, after 3 years of doing this, I realized that I was a victim of my own success in the sense that the activity was going really well, but I had too much work to be done. And the methods I've been using are really cutting edge on one hand, but on the other, because of being cutting edge, they have to be performed manually and are very error prone. And I had also the feeling of doing repetitive tasks, the same things over and over. So I had to find a solution also because I have very little time to do other things that interest me, like going to the seaside or eating the food that is something extremely good around here. So my solution to this problem was actually to start this company that is called Orestron and is still based in the same small town. So in order to solve the problem of having too much things to do and using manual methods, I started hiring people. Now we are 4, and it's people with heterogeneous skills in the sense that I have a mathematician that works with me, and he's a pure mathematician. He does only mathematics. Then I have a computer scientist, which can do things that I'm not able to do anymore, probably. And then there is another person who helps me with the administration. Then I started doing some focused research investments on how to improve those methods and how to automatize them, and came to the conclusion that I needed to develop some internal tools, which actually we have now. Like we have tools for automatic analysis of circuits and stuff like that. And it's working, to be honest. Now we can develop things much more faster. I mean, much faster than before. Then for the repetitive tasks, as Raquel, is it Raquel or Rachel? Raquel, I guess. Sorry, I don't remember the names. As she said before, we've developed a small library at the moment, but it's growing very fast, of reusable DSP modules, and that's available for licensing, but we'll talk about it later. So let's get to the technical stuff. Now, I've followed some, I mean, I've watched some of the previous meetups, and I've noticed that people usually get their hands dirty with code very fast, which is not my approach. So I will rather concentrate on the mathematical and engineering part. If it's too complicated, I guess not, but if it's too complicated, don't get scared. It's not important that you get all the details. It's just to show the process of developing something, how the reasoning goes. So let's say that we want to make a volume control, which is the most basic thing I could come up with. What you want to implement is something that respects this formula, which means that your output signal will be your input signal scaled by some factor, and you control this factor. So if you go and code this, you'll get something like this. In essence, that is, you will have a process function which will create this output. It will be passed an input buffer, an output buffer, this value, and a number that says how many samples you have in each buffer. And essentially, you will just apply the formula in an iterative fashion on all of the input values. It seems very easy. It's not. This has two big issues. So the first issue is that you probably have, I mean, if you do it as we've done before, you will have not respected Fechner's law or Fechner's law. Again, I don't know how to pronounce names. I'm reading too much, speaking too little lately. So this is a law developed, let's say, found out by a psychologist, whose name was Fechner or Fechner, I don't know, which essentially says that in our case, the perception of loudness is logarithmic with the actual intensity of the physical stimulus, which I can suppose it means nothing to some people, but in practice, it means we need to work on the decibel scale and not on the absolute values for this kind of things like volume. The decibel scale is defined as with a power law such as that's shown on the right side of the line here. And we'll make an example to make it a little bit more clear, perhaps. We know from experiments that to get a signal to be twice as loud as before, we need to increase it by around 10 decibels, which means multiplying the signal by a factor of 3.16 more or less, which is the square root of 10 if you wonder, but yeah, by that factor. If you want this signal to be 4 times louder, you should not multiply it by 2 times 3.16, but rather by 10, which is the square of 3.16. That's what the thing means actually in practice. Another way to see the same thing is if you have a linearly varying intensity parameter, which is represented on this graph by the blue line, you will have a loudness, you will perceive loudness to change much more rapidly when the value of this parameter is low rather than when it's high. If you want instead to have the loudness changing in a consistent fashion perceptually, you should rather use a power law such as the blue line on the right side of the, on the graph on the right side here. So that's not enough still, because if you do that, if you apply a power law such as the one that we've been talking before, the first problem that you have is that a power law can never reach 0 because the argument should be minus infinity. And you don't have that on a parameter or a knob or something like that. Another thing that you might notice is that a power law can be converted to and from an exponential law. That's useful. But if you want to solve this problem in a, let's say, correct fashion or an approachable fashion, you can also notice that you can scale more or less an exponential to force minimum, maximum, and midpoint values. And that solves the problem here. And also, this law is more or less specified as potentiometer behavior, is specified and not respected in reality, but that's how things are specified usually. So I can understand if all of this looks like black magic, but we can translate it into code very easily. So the result is, now we want to use rather than k, a function of k, and this function, if we want the midpoint to be 10%, you do all the calculations, you come up with this formula. So you just want to apply this formula here, the code, shows how it can be applied. Essentially, you can calculate it outside of the audio loop. And that's what that corresponds to the numbers that you have above, just a little bit of calculation done beforehand. And then you apply this thing. This solves one of the two problems. There is another problem left. And the problem is the problem of zipper noise, which means that controls in audio systems are usually updated at a lower rate than audio itself. So you will have a stepping effect that will sound horrible to most people, at least, yeah, unless you want to do it on purpose, but that's usually not the case. So what you want to do is to smooth out this staircase kind of thing. And that can be done. If you can do that, actually you get the thing on the right, which, as you can see, changes a little bit more smoothly. And indeed, this is called smoothing. And the simplest way to do this smoothing thing is to use something called a one-pole filter, which is the simplest filter you can program in DSP. So instead of using a function as before, now we want to use another signal. So we are multiplying two signals. And this signal is defined in the case of the one-pole filter as a time recursive function, which means that the value of this signal will depend on the previous value of the same signal, and you will do a little bit of math just to have this thing implemented properly. You will have as input the function that we've seen before, so we can respect the Fechner's law. And the value of these fixed coefficients that we have here, okay, I got a vocal message, whatever. The function that will, I mean, the constant that you have here can be computed in this way, which is one of the possible ways to do this. But I guess it's if you are into these things, it's the most correct for this kind of application, in my opinion. And it's a method called impulse invariant transfer or method or whatever, impulse invariance or something like that. You can find it on Wikipedia, by the way, so if you're interested. So let's put everything together. Now we will have, by the way, sorry, I forgot. This constant will depend on a couple of values. One is the sample rate, which is, well, the frequency at which the audio is updated, and that is known from the outside usually. And a value that you choose yourself, which I called tau here, and it's the time constant in some circuit. It's also called the time constant, and it basically determines how fast this filter will act, how much will it smooth. So we put everything together, and what we have here is the full code of the thing. We have, in this case, a global constant definition for the value tau, which in this case is 50 milliseconds, which means that to reach the final value, it will get from one step to another. It will take more or less 200 milliseconds. But I won't bore you with all these mathematical details, at least not more than I did already. Then you will probably have some functions to compute different things, like, for example, the sample rate is usually given very early when the plugin is instantiated or something like that, and it will not change. So probably we'll have a function like this set sample rate here, in which you can calculate your coefficient. Then you will probably have a function to reset the state of the system. Essentially here you will set the initial value to the initial volume value to some value that you like. I set 0 because it's fun. And then your process function will just be more or less like before, except that here you will have this implementation of this one-pole filter. This line actually computes the filter with the formula that we've seen before. And at the end of the function, we'll update the state. That's all. I hope that's clear, but if it's not, as I said, it doesn't matter. It's just to show the reasoning behind all of this. So this can be still optimized. This is not final and so on, but at least you get a glimpse of how the things work and how many little problems you have to solve every time you implement anything in DSP. And that's a simple example. Now I want to scale you off a little bit more, and we will try to do the same thing, but without the code, because otherwise it would get too long, for a Sallen-Key low-pass filter. So a Sallen-Key low-pass filter is the simplest musical filter you can use in a synthesizer or an effect. And it's made of 5 electronical components. So now we start from a real circuit, well, kind of real circuit, because it's never this easy, actually. But anyway, so if you go to Wikipedia and search Sallen-Key low-pass filter, you will get these one fantastic equations. The first one is called a transfer function of the filter. That is a mathematical description of what this filter does in linear terms. And then you will have expressions for the cutoff frequency and the Q value, which is, well, Q is called also quality factor, and it's directly linked to the resonance. It's a measure of how much the filter is resonant. And as you can see, those things depend more or less on all of the component values that you have in the circuit. So if you're very lucky, you will know the values of these components. They will be given to you. That's not the case in most cases, I would say. So the first thing that you should do, even before starting DSP, in my opinion, is to try to understand how to set these values if you're not given them. So in regular circuits, you have that capacitors have fixed values, while resistors don't, which means you will only be free to set resistors depending on controls from the users and not capacitors. Then what you would probably think is that we need to simplify a little bit the formula that we have before. And you can try by substituting some values, like expressing C1 in terms of C2, and expressing both resistance values in terms of a common resistance and some specific control values that I call V1 and V2 here. If you do that, those are the simplified formulas for the cutoff frequency and the quality factor. Of course, I don't know if you will find these formulas in textbooks or something like that. I hope so, but I had to compute them on my own for the presentation. So you don't have to be scared about these things if you want to really go hard into modeling circuits. Anyway, from this formula, from formulas, you can also deduct what are the minimum theoretical and maximum theoretical cutoff frequency and quality factors based on choosing the values of V1 and V2. And if you want to go completely insane, you can compute the values of V1 and V2 given cutoff frequency and quality factors of your choice. This is horrible, I know. Again, don't worry about the details here. What is interesting to notice, by the way, is that the cutoff frequency and the quality factor, that is the frequency and the resonance in this kind of circuit, cannot be independently set by changing only the value of one of the two resistors. So the things are coupled. And if you want to uncouple them, either you add more electronic components in the real circuit, or you have to control everything like digitally in one way or another. Of course, once you have full digital control, then you can also re-implement other, mappings for the parameters as you like, because you basically solved the parameter design problem. By the way, that was the first part. Then when you go to implementing these things, one of the issues that you have is that you have to approximate the derivatives that you have in the mathematical model of the circuit. And there are many possible choices. Here I show 3. Those are probably the most used ones. And these are not specific to DSP in any way. These are basically, they come from numerical integration, and they're common to a lot of mathematics, really, like numerical analysis and so on. And there are more, of course. And each of these formula will give you different results in terms of stability, accuracy, and time varying behavior of your DSP implementation of the, or let's say, digital implementation of the analog filter. So essentially, in this case, we have for the first 3 that the backwards Euler gives better stability, but worse accuracy, and the thing goes to the other part of the spectrum when you go downwards in this slide. But still, I mean, you should probably know some things about the properties of these things before choosing one. And if it was not enough, you can also choose to have different realizations of the filter, that is, different implementation styles. Those two are the most common and probably, but I don't want to say the most useful, but the most common when it comes to implementing second order digital filters like the Sallen-Key filter we have just seen, but they can be also used for higher order filters as long as they are linear. The one on the left is called direct form 1. The one on the right is called transposed direct form 2. But there are more. There is some forms that are called lattice filters or normalized ladder filters that has nothing to do with, you know, commercial ladder filters. Then there is another one which is perhaps more useful in this case, which is called topology preserving transform, I guess, if I remember correctly. I don't use it, so I don't remember the name, to be honest. And there are others. And again, choosing one over the other gives you different properties in terms of stability, time varying behavior, and whatnot. So again, you should know what you're doing basically here. Then finally, if it's not enough, all of what we've seen until now, there is also non-linear behavior. Now, this is also another complicated thing, perhaps even more complicated than the previous stuff. Essentially, in some circuits like this one, you will have one or two or three components that have non-linear behavior, which makes things extremely complicated computation-wise, but also this means that probably we have distortion added to your circuit, which will mean in general more harmonics will probably cause some aliasing noise to be generated, and you have to take that into account as well. You can do that by oversampling or by other special techniques. At least the minimum is that you need to know that this can happen. As I said before, nonlinearity means that you cannot use linear methods that are the most investigated in mathematics as of today. So not being able to resort to these methods means that certain things become complicated to compute. That's how things are. So all of these apart, let's say that we want to make a simple model just for fun or not to feel too ashamed of ourselves. So one thing that we could do is choose some values for the components. I made this arbitrary choice here of choosing C2 to be 1 microfarad. That's one number. You could choose another number. And if you choose K and R to have these values, then you have that the theoretical minimum cutoff frequency you can get is 10 Hertz. The maximum Q factor you can have is 20. But then you could restrict in practice your range for both values. And actually you probably want to have the cutoff frequency mapped in a logarithmic fashion because it works like the volume. We have the same thing with frequencies in our ears. So if you use those magic values, let's say, the formula will be a little bit simpler and you can actually define a mapping from input parameters normalized between 0 and 1 and actual cutoff frequency and Q values. When it comes to discretization and realization, I would suggest to start by only implementing linear behavior. That's complicated enough. To use backwards Euler discretization to get maximum possible stability, because that's usually a big problem with digital filters. To use a realization that's a little bit more complex than the simplest ones, like the TPT realization or something based on state space, because those help with stability as well, and not to forget smoothing for parameters, of course. So let's set all of these aside. That's the hardcore part in DSP, but you don't necessarily have to do all of that to create a product. You can actually get something ready-made, whether from us or from anybody else. That's not the point. So actually, we have developed this library that I was talking about before, and we have implemented something very simple. Let's say it's very simple after we have you have implemented it, which is an autofilter. That is a filter that modulates its own cutoff frequency, which is structurally relatively simple in the sense that we use the input signal to actually we feed the filter that we use in this product with the input signal, but we also have a drive section just before it. And then we use the same signal to feed an envelope follower, which controls the cutoff of the filter. Then we also have a separated LFO, which controls, again, the cutoff of the filter. And then the output of the filter goes into a dry-wet mix before the output. That's it. This is more or less inspired by a few real products that exist. One is fantastic, thanks. One is actually the ladder module by Moog. Then there is a guitar pedal which is called Meatball by Lofton, which is a fantastic autofilter by itself, and also the Boss Auto pedal is a product of this kind. We have implemented this thing with our library, and it's actually usable directly in the browser. You don't need to install anything. We just have custom DSP code there running on in the page, and it's compiled to WebAssembly. So we're not using any standard web audio stuff there. So I will show you the code of the process function for this little example. Essentially, we have this function takes an input buffer, an output buffer, a number of samples, as we've seen before. The first thing that we do here is to make a copy of the input signal. We've been extremely sloppy in doing it this way on the stack, but whatever, it was developed in very, very little time. Then we start with the LFO because it doesn't depend on anything. So essentially, we have a function that sets the frequency of the LFO, and this frequency is actually cubically mapped, which is a kind of exponential mapping as we've seen before, but not exactly. But yeah, essentially, LFO frequency is a parameter that is in 0-1 range, and the frequency that we set for the LFO goes from 0.1 Hertz to 20 Hertz. So the next thing that we do is to set some output coefficients. Essentially, our LFO module allows you to mix different waveforms together. So we just set the mixing values for each of these waveforms. And we have different cases. The first case is the sinusoidal case. So essentially, we set the sinusoid output factor to 1 and all the others to 0. Then we have the triangular waveform. Then we have, what is it here? The rectangular, let's say the pulse, reverse so, etc. Then we set the pulse width, which affects only the rectangular and triangular waveforms. Then we have our process function for the LFO. Essentially, here all the code is contained inside this function, and you don't need to go and code anything specific. In this case, I mean, in the case of this LFO module, we have many inputs and many outputs that are related to anti-aliasing, but we're not using them here, so it's all set to null. And then we take the last produced output sample as the actual LFO output. We could do it in a better way again, but we were doing everything in a hurry. Then here we use a one-pole filter to implement the envelope follower. Again, we have a threshold parameter on which we use a cubic mapping for its use to generate this the input for the envelope generator. And then we essentially do full wave rectification of the input, then we subtract the threshold and do half wave rectification. Essentially, this allows us to have an input that more or less resembles the loudness of, I mean, to have an input for the envelope generator that more or less is related to the loudness of the input. It's a small trick, but it works. And then we take, again, the output of the filter, the one-pole filter, as the output of the envelope generator. Then we have the drive section. Here we use a wave shaper class that has no special controls. So we need to do some gain staging before and after, and we also applied some smoothing. That's all about it. And then we finally have the filter section. So essentially we have two filters. One is a ladder filter and another is a wah filter. For the ladder filter, if it's been used the first time, we reset it, and then we set cutoff and resonant frequencies. Again, here the code is about mapping parameters and applying modulations. Then we have some gain staging, and we call the process function for the ladder filter. Instead, for the wah, well, instead it's similar. It's a similar thing for the wah. We set the wah position. Here we don't have a special control on the cutoff exactly, but rather on the wah the position of the wah pedal. Again, we apply modulations, we sum with the cutoff parameter. Then, if it's been executed the first time, we reset it and we process the signal. Finally, we have the smoothed dry wet mix. That's all. So, I don't know, maybe commenting all of this, it seems much, but essentially we could develop this thing in half an hour to an hour. I don't remember exactly. It was extremely fast. So, last two slides, I promise to not bore you too much. I just want to do a little bit of advertisement for the library that we're producing, just to tell you about the technical and the business aspects of it. So essentially, technically, we have developed something that we believe is very adaptable because it's developed in standard C. And we have also some optional C++ wrappers, but they are, as said, optional. We are not using the standard, not even the C standard library. There are no abstractions. We try to keep APIs as consistent as possible, but as said, without any common abstraction, there is even no notion of module inside the library. We do not use at the moment any CPU or platform specific code. If we will use it at some point, it will be optional as well. We've done some optimization, of course, on the code, and we give full source code access. We don't want to keep secrets with our clients. The thing is designed to be reusable in the sense that it's modular. There are many modules. Each is based on real world use cases. I mean, all of these came into existence because we didn't want to code anymore the same stuff over and over. The thing is very self-contained. The metaphor that we use is the usual patching metaphor that you can visually see, for example, in Pure Data Max and so on. The thing is easy to use, hopefully, easy to integrate in already existing projects or new projects, and documented. I mean, documented at this point, it's documented rather minimally, but we want also to produce some stuff that we publish on the website and perhaps videos, tutorials and whatnot. But I mean, we are only 4 people. It will take a little bit of time. The thing is robust, this I can guarantee, because each module is well defined. We've used scientific methodology from the start, so there is no trial and error going on. We know exactly what we want to achieve. Each module produces no side effects. So essentially nothing strange will happen outside of the module in any case. The thing is well tested and it's already used in production by our clients. So essentially there are musicians, probably many of them who are already using this stuff without knowing. And I want to say that we are trying to make this thing a good complement to existing UI libraries and frameworks like Juice, which is a sponsor today, and we do not want to overlap functionality in any way. When it comes to business aspects, we are rather liberal, perhaps too much, with the licensing, in the sense that we do not license the whole library at once, we just license single modules. We put no limits on the number of developers that can use it, or no limits on the number of products that can be developed using it. We offer an option for a time limit in the sense that you can either take it with no time limit, or if you want to spend less, you can have this low-cost option with a 5 years time limit. And you'll get free bug fixes in any case. We guess that this is, we made it useful as much as possible for hardware application, mobile software application, like mobile apps, desktop applications like plugins and so on. And it also works on the web. We want to to, I mean, we think this is a good option for independents, newcomer companies in this area, but also established companies as a mean to go faster, let's say, or to have newer and more reliable technology. There are many pros in our opinion. I won't go over them because you're bored and so am I. You can read them on the website. And finally, we also offer related custom services like ranging from just, let's say, education of some sort to the development of a full DSP engine. That's all. I hope you're still alive. This is our website. This is the email to contact us. We do not even have a newsletter at the moment. Everything is being rushed out as fast as possible, but we still live in Italy, so bureaucracy is trying to stop us in every possible way. That's all. Thanks.
That was awesome.
Thank
you. Brilliant.
Josh, you're muted.
Oh, wow. I was talking for about 10 seconds there and I was muted the whole time. Yes. So, yeah, a lot of people and a lot of activity in the chat with a couple questions. And Rachel, as a DSP person, if you have any questions, please feel free to interrupt me and fire away. So in the meantime, I have a couple questions. One question was that in the volume control, you talked about some other optimizations that you could make. And I was wondering if you could just talk a little bit about that. I was very curious to hear what that would look like.
Okay, so on the top of my head, what I remember from the example, one thing that could be done is to reduce the update rate in smoothing. So essentially, you don't need to actually smooth at every sample. You can get by smoothing, I don't know, each 4 samples, each 8 samples. Actually, this number should also depend on sample rate to do things properly. And that's one thing. The second thing is that you don't even need to use the standard library for computing the exponential, for example, because the standard math library that's used in programming language like C or C++ tends to prefer accuracy over performance. And in audio DSP, that's not our main concern, let's say. Those are the 2 things that come to mind. I don't know if there are others actually.
Yeah. So a few people have commented on this already, and I wanted to get your thoughts. So there was a question just in terms of avoiding the standard library, and how much of an optimization do you feel that is? Do you feel that that's a significant optimization? Do you feel that it's kind of a 1% difference that will just give you a little bit more power? What are your thoughts on that?
It depends how much you use from it and what you use exactly, but I can say that savings can be enormous, especially if you do nonlinear stuff. Like, for example, if you use the standard library to compute a hyperbolic tangent, which is very common, the thing will probably implement some iterative method to get the correct result. And the iterative method will contain looping, branching, all sorts of stuff that's stall the pipeline of the CPU. So I don't want to get too much in detail here, but the thing is that it will be worse than you can realize if you just execute that part of code and test it. If you put it inside the project, it's worse than that usually. So you can really save a lot.
Wow. Okay. And Samex80 asked, in your volume control example, how do you determine the tau? Is that just an arbitrary number that you pick, or how is that actually determined?
The answer is yes, it's arbitrary in the sense that you can use any value technically, but in practice, what you want to do is to feed this control with a sinusoid, possibly around 1 kilohertz. The reason, I mean, I know that this is a little bit a pragmatic approach, but I know that the sinusoid is the waveform that is more suffering from zipper noise over volume. And I don't know exactly what is the theoretical reason behind this, but it's more or less known among people who do audio DSP.
Okay. Sounds good. Jacques Laplatte asks, what is a good value in seconds to use for a sample buffer passed to these real-time filtering methods?
Sorry, I didn't quite get the question.
What would a good value in seconds be to use for a sample buffer? So how big should a sample buffer be to use for passing into these real-time filtering methods?
Okay, so I mean the methods, as I've shown here, do not introduce any latency, if that's one of the concerns. Of course, that's not always the case. For example, if you have resampling oversampling, you will perhaps introduce some of these. It depends also on the techniques that you use. But anyway, there is a sort of golden rule for, at least for guitar effects. You don't want to get over, let's say, 10 milliseconds, possibly even lower than that. But those 10 milliseconds include the whole chain. So it's a round trip latency measure. So you want to take into account operating system, sound card, host application, whatever is in between. So I would say usually you want something that is in the range of 2 to 5 milliseconds maximum, and you compute that by, dividing the number of samples by the sample rate.
Okay. Tugrul Akiz, and I'm sorry if I mispronounced your name, asks, I've seen ladder filters used a lot in synths. Are there applications for biquads or Chebyshev or Butterworth type filters as well in the audio technology world? And I guess the answer to that would be yes, they're quite common actually, right?
Yeah, they certainly are, but it depends on the application. Like I wouldn't never use a Butterworth filter in a synthesizer. It makes no sense. Mm-hmm. You want something that's resonant, otherwise where is the fun?
Yes. And Giova asks if you could suggest if there was somebody that wanted to get into this same path that you're in, what would you suggest as a good starting point? Where would you begin your path?
Well, if you want to be crazy like I was at the beginning, I would suggest to get an engineering degree and possibly in electronics, telecommunications, or if you're less lucky like me, in computer engineering, and go on from there. If you don't want to do that, buy some good mathematics and especially signal processing books.
Mm-hmm. Great. Any other thoughts or questions, Rachel?
I think that last question's like sort of answered what I was going to go for, but I just saw a few people in the chat were maybe a bit taken aback by the maths and thinking, okay, like where can I find these kind of projects where I'm like a first kind of virtual analog modeling project to get into, where they can find somewhere to learn how to obtain the analog transfer function and then apply something like the bilinear transform and take that into the digital domain. I was wondering if you have any like specific recommendations for projects or resources that might be helpful.
So essentially, if you want to know how to derive a transfer function, again, I would suggest to buy a good analog electronic books. That's not DSP specific in any way. So analog designers use those things all the time. I don't know, on the internet, you probably will find this information as well, perhaps even on Wikipedia or somewhere else. I don't know, because I did this stuff at university first, so I didn't search for myself. Then when it comes to the actual DSP part, there are some books or sources that I could recommend, of course. Even if as a beginner book, for example, I would suggest The Art of VA Design by Zavalishin. which is freely obtainable on the internet. That's a good book for starting out with these things. Once one gets a little bit more comfortable with this stuff, I would strongly suggest to avoid, how to say, certain types of literature and go straight to publications from, not the latest ones because they are a bit more complicated, but scientific publications from early 2000s or something, especially from the DAFEX conference or ICASP. I mean, any conference that deals with this stuff.
Great.
Thank you.
Leo asks if you've ever used Wave digital filters and your thoughts on them.
Yeah, that's an excellent question. I started with digital filters. Actually, I've published 2 or 3 papers on them. If you're curious, just go to my website or find me on Scholar, Google Scholar or ResearchGate, I don't know. But yeah, I've used them extensively, even extended the theory a little bit. At the beginning, I thought that there were a solution to everything. Then I realized that was not the case. Let's put it like this. They are good for modularity in the sense that you can build a circuit and then if you change your mind at a certain point, you can change the topology very easily. The bad part of them is that their time varying behavior is horrible, and it's horrible because of how they're built. So if you want to actually have a product that needs fast modulations, don't use wave digital filters.
Okay, great. And we got another question from Tugrul, who asks, he or she or they comment, what is interesting to me is that there are serious efforts to emulate analog devices that are not well designed with some old approaches. And the question is the sound of old devices a habit, or was it really that good?
It depends on what you define, how you define good or bad. But to my ears, at least, some things sound really nice. That's all I can say. Other things, not that much. It's more a matter of fashion. And I mean, if you ask me personally, I'm a kind of guy who listens mostly to jazz, rock, and stuff like that. So I will tell you that clear amplifiers, I like them a lot. And maybe certain synthesizers I don't. But if you ask another person, they have completely different tastes. So it's up to you.
Yeah, maybe it's that our musical landscape has been so colored by these devices and that they just naturally sound pleasing to us now more than anything. Yeah.
Absolutely.
I wonder if it would have, I wonder what it would be like if it was the reverse, where we started out in this digital domain and then we went back to analog devices, if those would sound more pleasing to us, or if they would sound not very interesting.
I don't know, but I can tell you one thing. I was just playing before this this little meetup with, Vice, the emulator of the C64, and I was listening to the actual sounds it produces, and it's remarkably close to the original thing. And I really like the noise of the Commodore 64, and I was using it when I was 3, 4, 5 years old. I guess that part of what we hear, if we like it or not, is related to our infancy, really. But you should ask a psychologist. I mean, that's certainly my experience. So perhaps if we were grown with digital technology, we wouldn't like analog one, possibly. I mean, it's very likely, maybe.
Yeah. Yeah, it's the question. Sometimes I think that, like when it comes to a band playing together, it's the humanization of when you hear the Beatles, for example, and things going a little bit faster or slower. And it's, in my opinion, sometimes it's the imperfections that really give it that sound that's so pleasing to our ears. And that when things are too regimented, that, I think as a music producer myself, that, we can hear the result when things are too regimented, when The hi-hats have no difference in velocity. Everything just comes out very mechanical and not very pleasing at all. So sometimes it feels that even though we're in the digital domain, that we're still trying to create the humanization by taking drums and maybe moving them off a little bit. And I find that very interesting, actually, that we actually put the effort into creating that thing that we sought to eliminate at one point in time, the imperfections.
Yeah, to add to that, Josh, I mean, I'm sorry I'm interrupting, but the proof is in the pudding. If you go to Reverb and you see the prices on old gear, even from simple digital machines like the SP-1200, and so you'll see it's like they started reissuing that with the original circuit. I mean, if one would logically think, what's the point to doing that? I mean, when you have such more refined circuits and perfected timings, it's all about, I think, two things probably. The simplicity of certain things also is very appealing. What is instant? Because the color is already done. Same with film. Like, why does Quentin Tarantino still prefer to shoot on film? What you just said, the imperfections, the impurity, there's the kind of certain color which we took for granted. And when digital came about, that we were stripped of that, right? So suddenly everything's naked, and it's like right there. And like you say, psychologically, as Stefano was saying, psychologists might be able to tell why human beings, like certain kind of stuff. Like he's saying, there's a noise in the Commodore 64. Commodore 64, again, being a completely digital device, but all the aliasing and the noise and the A to D converters and the signal to noise ratio was not perfect. The converters were not designed to be perfect, but that noise factor or whatever just comes to that. Even your own point of hip hop, like for example, there's people place space between the transients, like they will actually add a silence before that. So when you play the drums, how that imperfect sampling is what creates back that groove as to or I mean, me being such an analog person, I was dying to comment on that, so sorry to interrupt, but I think it has its value. It's people are buying that stuff.
Yeah, I think those are very valid points. Absolutely. It's so interesting. You could take it even further and say, well, why do we have a different type of connection? For instance, when we're meeting in person versus meeting on Zoom, it feels almost like that can be applied. Yeah, it's like that can be applied in a way to how we perceive sound as well. Why we find certain sounds to be very pleasing and resonating with us, and others to be not so much.
Lo-fi is a whole genre now. Tell me about it. I'm making products. It's all in demand genres. Like I was doing this, 4, 5 years ago, 6 years ago, adding this, and I was so badly battered sometimes. Who needs a product like this? Why are you adding? And I'm like, wait, give it 4, 5 years, and boom, people realize that it's a style now. It's stylistic.
We have 2 more questions and then we'll wrap up. One question from Giova asking if you're a musician. Do you produce? Do you play yourself?
Let's say no. It's the short answer.
No. Interesting.
I was playing bass until I was 20, let's say. Then less and less. I got to the point where I take my bass in my hands like once every month or something like that. So no, unluckily.
Okay, great. And Michael Kaufman asks, do you have any guidance in terms of when to avoid the standard library or anything like that? Or would you take an all or none type of approach?
I try to avoid this as much as possible, to be honest.
Yeah.
I know that there are some cases in which it's not that much of a problem, like certain mathematical functions are implemented directly by the CPU. That happens, but you need to be sure about which CPU your code runs on. So if you can avoid it, it's better, in my opinion.
And a person in the chat, Martin, mentioned this earlier, and I'll mention as well. There's actually a pretty good game audio talk about this. I don't remember where it's at, but it's actually a game audio talk where they discuss avoiding the standard library. I think it was from one of the game audio conferences, but they discussed that and their reasonings for that and various optimizations that they've made. So I'll try to find it and put it in the link in the description afterwards or something. But yeah, pretty interesting talk. I thought, wow, that's pretty deep.
Good. It means I'm not crazy.
Yeah, no. It's actually it's actually a pretty common practice within game audio when companies like Electronic Arts have their own version of the standard library, and I know music tech companies that do as well, where they have their own implementations of standard library functions. So, great, Stefano, thank you so much for that information. I know people found it really insightful, and yeah, I know that it's been a lot of fun and really educational for me as well.
Thank you for having me